A Markov chain with transition matrix P is said to be ergodic if P is regular. So that means there exists some n0 larger than or equal to 1, such that all the entries of P to the power n0 are strictly positive. Now, this condition means that it is possible with a strictly positive probability to go from one level I to another level j in the scale in a finite number of transitions. Or in other words, this means that all the states of the Markov chain are accessible from any initial state in a finite number of steps. All bonus-malus scales in practical use have a best level, with the property that a policy in that level remains in the same level after claim-free period. Now, in our framework, the best level is denoted as level 0, and for any level, it is then possible to reach this super bonus level 0 after a sufficiently large number of claim-free years, which then results in P L0 and then superscript n between brackets strictly larger than 0 for all sufficiently large n. So in the following, we're going to restrict our attention to such non-periodic bonus rows. So the transition matrix P theta associated with a bonus-malus scale is assumed to be regular. So there exists some integer n0 larger than or equal to 1, such that all the entries of the n0th power of the one-step transition matrix are strictly positive. That's an assumption that we're gonna make. If the Markov chain is ergodic, the stationary distribution is unique. And a natural question that arises concerns the long-term behavior of a bonus-malus system, because intuitively we expect that such a system will stabilize in the long run. Since the annual claim numbers have been assumed to be independent and identically distributed, each policyholder will ultimately stabilize around a sort of equilibrium level that corresponds to his expected annual claim frequency, and he will jump around this level. And to give some intuition with respect to this idea, we're going to compute the powers of the transition matrix P evaluated for theta equal to 0.1, and we're going to use the -1 top scale, which is a very simple example. So recall that the transition probabilities in the matrix P require a value for theta to be specified, where theta is the annual expected claim frequency of the policyholder. So let's use this theta equal to 10% in our example. And here is what we get when we specify the -1 top scale one-step transition matrix for this particular value of theta. So this just means that you take the expression for the matrix P that we derived before, you replace the theta with 10% and you do the calculations. And we're now going to calculate the second power of this matrix. And you see here the result. We do the third power, we do the fourth power, and we take the fifth power. So what you see here is that the expression of the transition matrix will remain the same for all powers k, which are larger than or equal to 5. And that means we reached the so-called stationary distribution of this BM scale. So it turns out that whatever the initial distribution is of policyholders across the levels in the scale, the proportion of policyholders occupying each of the levels in the scale remains unchanged after 5 years. So the distribution of the state random variable Lk will not change for k greater than or equal to 5. And this distribution is here denoted with P superscript k, and then we also refer to the theta, which is equal to 10% here. And we see that about 61% of the policyholders in the steady state distribution will be in level 0, 6.3% of all the policyholders will be in level 1, and so on. About 9.5% of the policyholders will be in the top level of the scale after 5 years. And the 5-step transition matrix, which was printed on the previous sheet, has this so-called steady state distribution or limit distribution in each of its rows. So what we see here is that after 5 years, the bonus-malus scale reaches this so-called stationary distribution. In the book, you can find similar calculations for the other toy example that we've been working with. That's the -1 + 2 scale. And for that particular BM scale, convergence to the stationary distribution is way slower compared to the example that we developed on the sheets. It ultimately converges, but it just goes slower. So let us consider the trajectory of a policyholder with expected claim frequency theta across the levels of the bonus-malus scale. And we're going to denote this stationary distribution of the scale with a notation p theta. And its components are p0 theta, p1 theta, and so on up to ps theta. That is the probability that a policyholder with expected claim frequency theta occupies level between 0 and s once the steady state of the BM system has been reached. And you can express each of these probabilities as the limit for n running to infinity of the n-step probability to go from a certain level L1 to a certain level L2. So the limit of this n-step probability, that should be equal to the limit distribution PL2 evaluated in theta. So in general, PL theta is the limit value of the probability that the policyholder is in level L when n goes to infinity. This also implies, as our example illustrates, that taking powers of the one-step probability matrix p theta ultimately converges to a matrix denoted here with p theta, where we have the same expression or the same distribution in each of the rows of this matrix, and that distribution is formed by the stationary distribution that we introduced over here. So the question is, how can we compute this steady state distribution? So how can we compute the PL theta probability? So the probability to ultimately be in level L of the scale when the bonus-malus system reached convergence. Calculating the power of the one-step transition matrix is not an option. It's not an efficient way to get these probabilities in the stationary distribution. We will therefore derive a more efficient approach on this sheet and on the next one to calculate this limit distribution. And first of all, we already demonstrated that the n+1 step probability, the Pij n+1 theta, that can be expressed as shown here on the sheet. And we hereby use the n-step probabilities and we use the one-step probabilities. Now, if you take the limit for n going to infinity at both sides of this equation, then that leads to the following relation, the following expression between the Pj probabilities and these PL probabilities where L runs from 0 to S. Indeed, the limit of the n+1 step and the n-step transition probabilities, that will both be denoted with this Pj, respectively PL theta. In matrix notation, this limit result implies the following set of equations. Moreover, the product of your pi distribution, pi transpose distribution, and a vector E, which is a column vector completely filled with ones, the product of these two, that should be equal to 1. And that's true because the pi probabilities, they determine a distribution, so the entries of this distribution, of this vector, should all sum to 1. So what we see here is that we recognize this pi, this P distribution, as the left eigenvector of the matrix P. And these insights bring us to a direct method to get the stationary distribution pi theta. Let E be a matrix of dimension s plus 1, which is completely filled with ones. Then we, under the assumption that the matrix P, the transition matrix, is regular, the matrix, the identity matrix minus the P matrix plus the matrix E is invertible, and you can get the limit distribution, the pi distribution, as follows, as printed here on the sheet. So we're not going to give a proof of this result. You can find it in the book by Dundee et al. But it's a very workable way, a very workable solution to find the limit distribution once the steady state of the BM scale has been reached. So we're going to illustrate this recipe, this calculation, using the -1 top scale that we used earlier on. So here, the system needs 5 years to reach stationarity. We've seen it before. So if you would here do the calculation of this formula, you will see that you retrieve the limit distribution that we found earlier on. So we retrieve the stationary distribution pi for an a priori expected mean claim frequency equal to 10%. It's exactly, you get here exactly the same distribution as the one we obtained before by taking the powers of the transition matrix. And naturally, the recipe developed here is computationally more efficient as it avoids powering the transition matrix until convergence. So this ends the video about the long-term behavior of the BM scale. And one of the take-home messages is that we also found a computationally efficient way to calculate this steady-state distribution, to calculate this limit distribution.